from this, actually what we have shown is that a BFS is a vertex, which I have already shown, but probably I did it in this terms, so let's do it once more. Okay? Why is BFS a vertex? Suppose it is not. That means, so let's say my BFS is subpoint P. By contradiction, suppose P is not a vertex. What does that mean? What does it mean? There is points Q and R, both of them are feasible such that P is a convex combination, right? So what do I know about Q and R? Q remember our intuition, right? If whatever coordinates of P are 0, all those coordinates in Q and R should also be 0. Because I know that every entry of Q is positive, and when I take the convex combination, it will remain positive. Questions? Right? So that means this implies now that AS XS is equal to B has 3 solutions. PS, QS, RS. This is what we did here exactly. I'm just repeating my argument. Questions about this? This was the easy direction. So if you are not happy with this, then it's time to take a break. Not from you or me speaking, but I mean, we won't move forward. But this, remember, from the 2 dimensions, we got this idea that, oh, you know, look at the coordinates which are zeros. The remaining ones, if they create an invertible thing, we are happy. With that idea, we defined a basic feasible solution, and we are hoping that it characterizes vertex. And from this idea, actually, it was already clear that a BFS is a vertex, and I have formally written down the proof here, right? But the other important thing where we should keep our fingers crossed is if every vertex is a BFS. Because then we would be happy. Then we have a mathematical characterization of a vertex. And now you see, this description is way nicer than saying, oh, there are 2 points, there are no 2 points whose convex combination is this point. This is much more concrete description of a vertex as compared to our previous general description. And we could get this because our feasible region was of this special form. Right? This is not general true for any vertex of any kind of a shape or something, right? This we are able to do because we are talking about Ax equal to B, x greater than equal to C. Good. So what we want to prove now is vertex is a BFS. And why don't we give Dev the chance to prove this? It's okay, you let him sleep. So, it's okay, it's okay. So, what we want to prove is that a vertex is also a BFS. We have proved that BFS is a vertex, but how do we prove that a vertex is a BFS? This is not clear from what we did right now. Right? Okay, good. But what we know is, okay, so let's look at point P. Let's say it is a vertex. We know that P is a vertex, and we want to look at columns which correspond to entries of P which are non-zero, right? Remember the old ideas. Here what we looked at was all the columns which corresponded to the non-zero entries of P, and here they were invertible. right? So say S is the set of I such that Pi equal to 0, or let's keep our notation like this, define S, sorry. So to prove that P is a BFS, what do we need to show? You have the definition of basic feasible solution, BFS written there. Tell me, what do I need to show so that I show that P is a BFS? Very nice. What I need to show is that or in other words, right? Notice that if there are very few columns in AS which are linearly independent, they are not M, I can just join arbitrary columns of columns and make them M, right? So that I get the complete. So the only description, only difference between this, or actually between this equivalence, is that it might happen that AS is not full rank, right? It is not the size of S is less than. I know size of S cannot be more than M because of the rank constraint, right? No AS in A can have rank more than M because the rank of A is M itself, right? But this equivalence, like this is almost equivalence, because it might happen that AS has less number of columns, so it's not like a M cross M matrix. But that's okay, then I can pick up arbitrary columns of A which are remaining and make it a complete rank. The corresponding entries of that will be 0, it doesn't matter. Here I am not saying that the xi for I element of S has to be non-zero. Is it okay? The only constraint here is that the non-basic variables have to be 0. Basic variables could be 0, might not be non-zero. That's okay. That will be the unique solution which comes out from this. It might have some more zeros. So this again will correspond to that case. It might turn out that I only need M minus 1 columns. Those are linearly independent. They give me a solution. The rest, the next column, it doesn't matter because that will anyway be multiplied by 0. That's okay. My B is a combination of M minus 1 columns. That can happen completely fine. Okay. So this is what we want to show. If I find out that columns of AS are linearly independent, I can convert it into a BFS. If size of S is equal to M, great. If it is not, just add arbitrary columns. And this you can convince yourself. Okay. This is a small trivial technicality, but if you are stuck with it, you can ask me after the class. This is okay. Sounds good? So this is what we want to check now. You probably would not have cared if I hadn't pointed out this technicality, this equality, but now I have pointed out, but it's not a big deal. We can take care of it. So this is what. So then assume they are linearly dependent. There exist alpha is such that I element of this is what it means. Oh, Ci is the ith column of. Should I denote it by AI? Will that help? Or that's okay, right? So this How is that useful? Can you find more solutions of Remember, what were the solutions of Ax equal to b? You take a solution and add Ax equal to 0 solutions. What is this? This is the solution of No. We want to prove. This is to prove. That means I want to prove that these columns are linearly independent. This is my task now. Assume for contradiction they are linearly dependent, and I will come up with a contradiction. So assume that these columns, because if they are linearly independent, I am good. I have the BFS. If they are linearly dependent, I want to show there is a contradiction. So if they are linearly independent, but linearly dependent, by definition, there has to exist alpha such that their linear combination is 0. My claim is this will show that your original point is not a vertex. Can you give me more solutions of, so we already have one solution for this, right, which is P. Agreed? This is what it means. P is a vertex, S was the set where it was non-zero. So ASPS was B, right? Because Pn was 0, right? Again, I will write this, Pn is 0, this means this. So I already have a solution of this. Now what does alpha allow me to do? Add not just alpha, right? This is a solution of X. But how is it helpful? We wanted feasible points in this. What is the guarantee that these are positive?
It will have a minimum and we can take t to be this.
Exactly. All coordinates and P are positive. Now we are going to use that. Since all coordinates are positive, there exists small enough t such that P plus minus T alpha is greater than. And why is that a contradiction?
T minus T alpha and T plus T alpha.
Yeah, exactly. Because P is a convex combination, right? And if I want to what we have been able to prove is a very nice characterization of what a vertex is, and this nice characterization was possible because this was the feasible set. Okay. So if my feasible set is of this kind, I can define my BFS. What were the two conditions? Xi should be 0 for non-basic variables, and if I look at And if I look at the columns corresponding to the basic variables,